Jai Hind everyone, I am Shruti Jain, Assistant Professor, MCA Department from Ajay Kumar Garg Engineering College, Ghaziabad. The topic that I am going to discuss today is I/O management and disk scheduling. This topic is covered under the subject operating system and the subject code is KCA 203. The target students over here are MCA second semester first year students. So coming to what I/O devices or I/O management is. So we know that the control of the devices is that are connected to the computer. That is a major concern of operating system design because I/O devices vary so widely in their functions and speed. So we need a variety of methods to control them. Now if we talk about the current I/O devices technology, it exhibits two conflicting trends. The first one is we see that there is an increase in the standardization of the software and the hardware interfaces. Like if we talk about few years back, we need to have different ports for different devices, but now we have a standardized USB port that is used for most of the hardware devices. So this trend help us to incorporate improved device generation into existing computers and operating system. On the other hand, there is an increased broad variety of I/O devices. Some new devices are so unlike previous devices that it is a challenge to incorporate them to the computers or the operating system because the technology is changing day by day. So this challenge is met by a combination of hardware and software techniques. So the basic I/O device elements that we are talking about, like ports, buses, device controllers, they accommodate a wide variety of I/O devices. So to encapsulate the detail and the audacity of the different devices, the kernel of the operating system is structured to use device driver modules. So coming to what I/O hardware is, so the I/O devices, they can be roughly categorized as storage, communications, user interface and others. Devices communicate through signals that are sent through wires or through air, that is a Wi-Fi. Then the devices that connect with the computers via ports, those are the serial or the parallel ports that we already know. So we have a common set of wires that are connecting multiple devices, that is a bus. Now we have different types of buses. They include rigid protocols for the type of message that can be sent across a bus and the procedures for resolving the contention issues. So if we look over here, we have a figure which talks about different buses. So the first bus that we have is a PCI bus which connects the high level, high speed, high bandwidth devices to memory subsystems and the CPU. So if we look here, the PCI bus, which is a very high frequency bus, which high speed, high bandwidth devices are connected through this bus. The next one is the expansion bus, which connects the slower or low bandwidth devices which typically deliver data one character at a time, maybe with buffering. So we have the expansion bus interface over here which connects, we have this expansion bus which connects the low bandwidth devices, like we have the keyboard or bus interface, these kind of things. Then we have SCSI bus which connects several SCSI devices to common SCSI controller. So we have this SCSI controller and the SCSI bus which connects different disks together and then it helps in the transmission of data. The next one that we have is a daisy chain bus, in which is when a string of devices is connected like the beads of a chain, and only one of the devices directly connected to the host. So these are the different types of buses which helps in communicating with the different devices like cache, memory, processor, monitor, graphic controller, etc. Now the next topic that is there is DMA, that is direct memory access. So for devices which transfer large quantity of data, it is wasteful to tie up the CPU transferring data in and out of the registers one byte at a time. So this work can be offloaded to a special process that is known as direct memory access or DMA controller, where the host issues a command to the DMA controller indicating the location where the data is located, the location where the data is to be transferred to and the number of bytes of the data to transfer. So the DMA controller, it handles the data transfer and then interrupts the CPU when the transfer is complete. So if we talk about a simple DMA controller, it is a standard component in modern PCs, and many bus mastering IO cards contain their own DMA hardware. Now we have another concept that is known as the handshaking. So handshaking between DMA controllers and their devices is accomplished through two wires called DMA request and DMA acknowledge wires. So handshaking is a process where once the request is generated, it is being acknowledged by the other side, and then only the data transmission takes place. So while the DMA transfer is going on, the CPU does not have access to PCI bus that includes a main memory. But yes, it does have an access to internal registers and primary and secondary caches. So DMA can be done in terms of either physical addresses or the virtual addresses that are mapped to physical addresses. So this later approach, that is through virtual address, that is known as direct virtual memory access or DVMA, and it allows a direct data transfer from one memory mapped device to another without using any main memory chips. So if we direct DMA access by the user processes, they can speed up the operations, but is generally forbidden by modern systems for security and protection reasons. That is, DMA is a kernel mode operation. So we have a 6-step process to perform the DMA transfer. The first one is the device driver is told to transfer the disk data to buffer at the address X. Now after that, the device driver will tell the disk controller to transfer some number of bytes from disk to buffer at address X. So once that is done, at step 3, the disk controller, it will initiate the DMA transfer and will send each byte to the DMA controller. Now when each byte is sent, we have a counter variable C, which will take care of the transferring of the byte. So the DMA controller will transfer the byte to buffer X, which increases the memory address and decreases C until C equal to 0. Once the value of C is equal to 0, it tells that the signal transfer is completed. If the value of C is not equal to 0, in that case it is assumed that some more bytes are yet to be transferred. Now blocking and non-blocking IO. When we are talking about the blocking IO, a process is moved to the wait queue when the IO request is made. That means whenever any process enters into the system and it requires for the usage of any IO device, an interrupt is generated and the process is moved to the wait queue until and unless that IO device is accessed, and then it comes to the ready queue. But when it is about the non-blocking IO, the IO request returns immediately whether the requested IO operation has occurred or not. So in that case, what happens is, a process is divided into multi-threads and one of the thread goes and initiate the IO interrupt. When that IO interrupt is initiated, only the request is sent and the process will continue doing rest of the things. So we have an approach of multi-threading applications in which one thread makes blocking IO calls, that we have seen over here, that when you block the IO call, the process has to wait. But here the process will be waiting only by one thread. The whole of the process will not come at and get halted, while other threads continue to update the screen and perform the. So scheduling IO requests, they can greatly improve overall efficiency. Priorities can also play an important part in request scheduling. Buffering and caching can also help and allow for more flexible scheduling options. So we have a concept of buffering where it talks about 3 different reasons. The first one is the speed buffering. The speed differences between 2 devices. So because we have the speed differences between 2 devices, so a slower device may write data into a buffer, and when the buffer is full, the entire buffer is sent to the fast device all at once, and then the other buffers start buffering the data. So in that case, we need 2 buffers, and that is why it is known as double buffering, where we need 2 buffers to transfer the data from from a slow buffer to a faster device. The other part is the data transfer, because data transfer sizes also differ. So buffers are used in particular in networking systems to break the messages into smaller packets for transfer and then for reassembling at the receiving side. The third one is to support copy semantics. For example, when an application requires a disk write, the data is copied from user's memory area into the kernel buffer. Now that application can change their copy of data, but the data that eventually gets written onto the disk is a version of the data at the time the write request was made, and the data change will not be reflected into the buffer. Coming to caching, it also involves keeping a copy of data in the faster access location than where the data is normally stored. So buffering and caching are very similar, except that a buffer may hold only a copy of a given data item, but cache is just a duplicate copy of some other data that is stored somewhere else. Also, the difference goes hand in hand, and they often share the same storage space, which may be used for both the purposes. For example, after a buffer is written to the disk, then the copy in the memory can be used as a cache copy. The next concept is spooling and device reservation. So spool, it is simultaneous peripheral operations online. It buffers the data from peripheral devices such as printers that cannot support interleaved data stream. So if we have multiple processes, they want to print at the same time, each of them will send their print data to files stored in the spool directory. When each file is closed, then the application sees that print job as complete, and the print scheduler will send each file to appropriate printer one at a time. Then support is provided by viewing the spool queues, removing jobs from queues, moving jobs from one queue to another, and so on. So operating systems can also provide support for processes to get exclusive access to particular devices, or wait until a device becomes available. I/O protection. The I/O system must protect against either the accidental or deliberate erroneous I/Os. So user applications are not allowed to perform the I/Os in the user mode. All I/O requests are handled through the kernel mode. Memory mapped areas and I/O ports must be protected by the memory management system, but access to these areas, they cannot be denied by the user programs. Now coming to the next topic, that is mass storage system. So we need a storage device that is used in a computer to store the information. It will retain this information when the computer is switched off. The type of the storage device that is used, it varies based on the type of the data and the rate at which it is created and used. So some examples of storage devices are the hard disk, CD-ROM, magnetic tape, removable media, etc. Coming to disk structure, so disk devices, these are addressed as large one-dimensional arrays of logical blocks, where the logical block is the smallest unit of transfer. The one-dimensional array of logical block is mapped into the sector of disk sequentially. So the sector 0 is the first sector of the first track of the outermost cylinder. Then mapping proceeds in order through that track, then rest of the tracks in that cylinder, and then through rest of the cylinders from outermost to innermost. So if we look over here, we have this as a spindle, and the rotation is going on in this direction. So rewrite head is present over here, and here we have the arm assembly. This is the different sectors, where this is sector S. So this is the track and the cylinder through which all these are connected. So this is how the disk structure works, and the data is written from one sector to another structure. Another sector. Next is disk scheduling. Now operating system is responsible for using the hardware efficiently for disk drivers. This means having the fast access time and disk bandwidth. So access time has two major components. The first one is the seek time and the other one is a rotational latency. So seek time is the time for the disk arm to move the head to the cylinder containing the desired sector. So at what sector you want to put your disk arm to, that is the time taken for the disk arm to move to that desired sector. Rotational latency is the additional time waiting for the disk to rotate the desired sector to the disk head. So rotational latency is basically related to this rotation, and seek time is related to placement of arm to a particular sector on which we require. So our task is to minimize the seek time, and the seek time is basically proportional to seek distance. That means the arm distance is traveling to what distance, basically that is equivalent to the seek time. So if the desired disk drive and controller are available, the request can be served immediately. If the device or the controller is busy, and any new request for the service will be placed on the queue of the pending request for that drive. For a multi-programming system with many processes, the disk queue may often have several pending requests. Thus, when one request is completed, the operating system chooses which pending request to service next. Several algorithms exist to schedule the servicing of the disk I/O requests. We illustrate them as a request queue. So we have the data from 0 to 199 where we have this as the request queue and the head pointer is pointed at 53. So the first algorithm that we have, the disk scheduling algorithm, is first come first serve. So here what happens, it will start pointing from 53 to the queue in the sequence in which the data is given to us. So from 53, it will go to 98 first, then to 183, then to 37, 122, 14, 124, 65 and 67. So in that case, what is happening? If we look over here, we have the jump from 37 to 122, 14 to 124 and 65. So instead, if we had the data that is coming in a sequence, then there will be shorter shifts between the two. Just see how the data is moving in this zigzag form. So the while swing from 122 to 14 and then back to 124 illustrate the problem with the schedule. So if the request for cylinder 37 and 14 could be serviced together before or after the request of 122 and 124, the total head movement could be decreased, and if the total head movement can be decreased, then in that case the seek time will also decrease. So for that, we have the shortest seek time first algorithm which selects the request with a minimum seek time from the current head position. Since the seek time increases with the number of cylinders traversed by the head, SSTF chooses a pending request closest to the current head position. It gives a substantial improvement to the performance. It is essentially a form of the shortest job first scheduling, and like SJF scheduling, it can cause starvation of some of the requests. So if we look over here, we have 53 as the head start, and then it will check for the closest value to 53. So for that we have 65 and then 67. So we have 65, 67 over here. Then after 65, 67, the next closest value is, we'll find a difference because we have 37 and 98. So if we find the difference of 67 and 37, we'll get the difference of 30. And if we find the difference of 98 and 67, we'll get a difference of 31. So it will, the next value that is to be traversed is 37, then 14. And then it will come to 98, 122, 124 and leaves at the last as 183. So here the movement is reduced as compared to the first come first serve. The next scheduling that we have is a scan scheduling where the disk arm starts at one end of the disk and it moves towards the other end, servicing the request as it reaches each cylinder until it gets to the other end of the disk. And at the other end, the direction of the head movement is reversed. So if it starts from 53, it will move to 37 till 0 here, and then it will again start towards the other direction. If we talk about the C-scan scheduling, in C-scan scheduling, it will first go to the last, and then it will not traverse any of the disk head over here. It will come to the top, first position and then again start traversing the data. That is the difference between scan and C-scan. Now, how do we select the disk scheduling algorithm? So, the amount of seeking required while accessing a file, it depends on where on the disk a file blocks are located. So, in order to access a file, directories and other file metadata, they have to be accessed to. So, it is helpful to locate metadata close to the file data, and also it is helpful to cache file metadata in primary memory. Different algorithms may be preferable depending on the details on how the file system is implemented. So, in modern disk, there may be bad blocks that are unused, and so the logical disk block address may not be the actual physical disk block number. The disk scheduling algorithm may be implemented in controller instead of the operating system because the controller is aware of the physical locations of the file blocks, and therefore is able to better optimize the rotational latency and the seek time. Thank you. That's all for today.